In the last section, we introduced DC circuits. Now we're going to further our discussion with some more interesting concepts. And the first thing we're going to talk about is Kirchhoff's laws. Kirchhoff's has two laws. He has KCL and KVL. KCL is Kirchhoff's junction rule or Kirchhoff's current rule, and KVL is Kirchhoff's loop rule or Kirchhoff's voltage law. Now, what do these two mean? Kirchhoff's junction rule says that current going into a node must be equal to current going out of a node. So let's say we have this. We have a voltage source, resistor here, we have this. We have R1, R2, R3. KCL, what goes in must come out, and this applies for current, so think C. So let's say we have I1 through here, the current going through the resistor, and it goes to this node. Nodes are points connected by wire without resistors or capacitors in between them. So this right here is a node. So going into this node, we have I1. Going out of it, we have I2 and I3. The current must escape somewhere. So since what goes in must come out, I1, what goes in, must be equal to I2 plus I3, or what goes out. And of course, you can solve for these values using Ohm's law, V equals IR. Voltage equals current times resistance. Okay, so we got KCL down. Now let's talk about KVL. Kirchhoff's voltage law. Alright, let's say we have this, a voltage source and a resistor. KVL, or Kirchhoff's loop rule, tells us that voltage drops around the loop must equal 0. Now this might seem confusing, but let's talk about it. So, we have a voltage rise because of the battery, which we're going to label V, battery, and then we're going to have a voltage drop across the resistor because when current travels through a resistor, voltage is lost. So the voltage drop represents here is voltage across the resistor. So, using Kirchhoff's voltage law, Kirchhoff's loop rule, we can draw a circle around a loop. It can be any circle, as long as the start and end points are the same point. So we start here, we go around, and we have a voltage rise. We know that voltage around a loop, the voltage drops must be 0, so we're going to set it equals 0. And we have a voltage rise, so we're going to add VB. Okay, so we're VB up, and we're going to keep going around. We get to VR. It's a voltage drop, so we subtract it, and we get back to the original point. This tells us that the voltage rise across the battery must be equal to the voltage drop across the resistor. If we know one of these, we can solve for the other one. And this is Kirchhoff's loop rule, Kirchhoff's voltage law, KVL. Okay, so we talked about batteries. Imagine your AA battery right here. We also can label this as a battery. If we put two batteries in series, the voltages add together. So let's put a 2-volt battery, or 2-volt voltage source, in series with a 3-volt voltage source. So we have 2 volts and 3 volts. Finding the equivalent voltage rise, we add them together. 2 plus 3 equals 5 volts. And this is for batteries or voltage sources in series. Okay, So, we have capacitors. We talked about that in an earlier section. And there's all these different equations for capacitors. So we're going to talk about the capacitor equations. Okay. So we know that capacitors hold charge. So we have our voltage source right here. And we have a switch that can be opened or closed. It keeps going around the wire, gets to our capacitor. We have a resistor. Goes back to the negative end of the battery. RC epsilon, which is voltage, and we have current going through it. So, at the moment we close this switch, voltage is going to go to the capacitor. It's going to charge the capacitor. So there are three equations I want you to remember, and these three equations are going to be tested. So 1, 2, 3. First is the voltage of the capacitor is equal to epsilon, voltage of the battery, times 1 minus E, which E is just the constant we all know. It's 2.2 something. It's in your calculator. To the power of negative T, which is time over RC. Solving for this, the capacitor charging, with the capacitor initially discharged with 0 voltage, let's just solve for certain constants. The second one is current equals, we know current is the change in charge over the change in time, so change in charge over change in time, derivatives, is equal to epsilon, the battery voltage, over the resistance, times E, which is the natural constant, times negative T over RC. And the third equation is charge equals capacitance times epsilon times 1 minus E to the negative T over RC. So all these different equations, I would suggest writing them down, memorizing them. Let's just solve for different constants. Now, this is for charging. But what if the capacitor is fully charged? What then? So then we're going to discharge it. Allow a charge to flow out of the capacitor. We have our resistance right here, our switch, the capacitor, resistance, capacitor, and we have our voltage source. And we have our current flowing. Once again, we have three equations. First equation is the voltage of the capacitor equals the initial voltage of the capacitor at time equals 0 times E to the negative T over RC. This represents the change in voltage of the capacitor over time if we allow voltage or current to flow from the capacitor to the opposite end, discharging the capacitor. The second equation is current, right here, equals I naught, which is the initial current when the capacitor begins to discharge, times E. E we know is the natural constant in your calculator. It's in your calculator. Times negative T over RC. And the final equation is charge equals initial charge. All this initial is the charge, current, voltage of when the capacitor starts to discharge, times E to the negative T over RC. And this is for discharging. So you're going to notice a theme. We always use RC. And this is because RC is equal to tau. Tau is the time constant. The time constant represents the time required for the capacitor to reach 63% of its full charge, or full voltage. That means in this situation, we have a capacitor that has no charge. We start charging it. At time tau, we find that by multiplying the resistance times the capacitance. At that time, the capacitor has 63% of its maximum charge. You might be tested, so just know RC, 63% of full charge.